Ever pondered how computers learn to classify data? Well, one of the fascinating ways they do this is through a method known as the support vector machine. In the world of machine learning and artificial intelligence, support vector machine, or SVM, stands as a powerful tool for classification, regression, and outlier detection. It's a concept that might seem complex, but let's unravel it together, step by step. First, imagine you're at a party and you want to separate the guests into two groups. You could draw a line between them, right? That's essentially what SVM does, but with data. It creates a hyperplane, or decision boundary, to split the data into different classes. Now, on to the second step. How does SVM decide where to draw this line? It aims to maximize the margin between the classes. The margin is the distance between the line and the nearest data point from each class. SVM's goal is to make this margin as wide as possible. That's why it's often called a maximum margin classifier. For the third step, let's introduce the support vectors. These are the data points that lie closest to the decision boundary. They're crucial because they directly influence the position and orientation of the decision boundary. Essentially, these vectors are the support for the SVM. But what happens when the data isn't easily separable? That's where the fourth step, the kernel trick, comes in. This technique allows SVM to handle non-linearly separable data by transforming it into a higher dimensional space where it is separable. It's like adding a third dimension to our party, allowing us to split the guests using a plane instead of a line. Finally, SVM uses a process called quadratic programming to find the optimal hyperplane. This is a complex mathematical method that ensures the decision boundary is the best possible one for classifying the data. So, to summarize, SVM operates in 5 steps. It begins by drawing a decision boundary, or hyperplane. It then maximizes the margin between classes and identifies the support vectors that influence this boundary. If the data isn't easily separable, SVM uses the kernel trick to transform it. Finally, it uses quadratic programming to find the optimal hyperplane. By following these steps, SVM provides an effective and versatile tool for machine learning, allowing computers to classify data with high accuracy. Understanding the methodology of the support vector machine is a step forward in comprehending how machine learning and artificial intelligence work. It's a fascinating journey, revealing how computers learn from data and make predictions that can help in various fields, from healthcare to finance, and even entertainment. So the next time you're at a party, remember the SVM. It's not just about drawing a line between guests, but about finding the best possible line that ensures everyone's in the right group. You might not be classifying data, but you're using the same logic, the same step-by-step method that SVM uses. It's a testament to how machine learning is not just about complex algorithms, but also about simple, everyday decisions. Let's take a moment to appreciate the brilliant minds behind the support vector machine. While we often marvel at the outcomes of machine learning, we seldom take a step back to acknowledge its history. The support vector machine was developed by Vladimir Vapnik and Alexei Chervonenkis during their work at AT&T Bell Labs in the 1990s. This was a pivotal time in the field of machine learning and artificial intelligence, and SVM was a significant breakthrough, a part of their innovative theory of learning from examples. This concept was novel at that time and has since been widely recognized and used in various fields, including medicine. So as we continue to embrace the complexities and capabilities of SVM, let's not forget to honor the intellectual prowess that brought us here. Having acknowledged the history of SVM, it's time to shift our focus to one of the most impactful applications of SVM, which is in the field of medicine. SVM has proven to be quite a game changer in this domain. One of the key areas where it has been used is disease prediction and diagnosis. For instance, in the case of cancer detection, SVM can analyze medical images and classify them as benign or malignant based on their distinguishing features. This process, driven by SVM, has greatly improved the accuracy and speed of diagnosis. The time saved due to this technology has been crucial in providing timely treatment, thus saving countless lives. The ability of SVM to learn from data and make accurate predictions has indeed made it an invaluable tool in the medical field, and we can only expect its usage to grow in the future. So, as we delve further into the world of SVM, it's exciting to see where else this powerful tool can be applied.